Mark and I are at Golden Gardens Park, at the beach in Golden Gardens Park in Seattle, Washington for this episode. And we're going to introduce 4 more rules of inference, starting with simplification. Simplification, abbreviated SIMP, may be understood this way. It says that if you have a statement of the form P ampersand Q, you may infer from that the P part of the P ampersand Q. And since the rule has 2 parts, it also says if you have a statement of the form P ampersand Q, you may infer the Q part of the P ampersand Q. So I'll test Mark on this. Suppose I had a statement of the form, a statement A ampersand E. Is that an instance of P ampersand Q?
Yes.
Thank you.
It fits the pattern.
Thank you. The P is replaced by?
The A.
Q is replaced by?
The E.
Okay. And then the rule says that from that I could infer the A. And that's simplification. Or if I had, suppose I had a W ampersand G. That's of the form P ampersand Q. Mm-hmm. So I could infer from that the Q part of the P ampersand Q, which would be the G. And that's how you do simplification. Does that make sense?
Yeah, it's simple.
Okay, simple. Mm-hmm. Is that a pun?
No.
The next rule is called conjunction, abbreviated CONJ. And conjunction says that if I have a line P and another line Q, that I may infer the conjunction of those 2 lines, P ampersand Q. In other words, I can take a line of a proof and another line of a proof, and I can join them together with an ampersand in the middle. You have to be careful. You have to follow these rules exactly as they're written. When you take 2 lines of a proof and join them together, it has to be an ampersand that joins them. Can't be a wedge, can't be a horseshoe, can't be any other formula. So there's 2 of the 4 inference rules we're going to introduce. And Mark's sort of helping me hold this because it has a tendency to blow over if we don't.
To be recycled.
And we'll recycle those. And the next rule of the 4 is called addition, abbreviated add. And it says that if given a statement P, we're allowed to infer from that the statement formed by repeating the P in its entirety, writing a wedge to the right of it, and then adding any statement we wish, call it Q. So from P we're allowed to infer P wedge Q, where Q is any statement at all.
That doesn't seem like it's cheating, just pulling Q out of thin air.
It does look at first like there's something fishy. But if you think about it, given that P is true, P wedge anything must be true, because a wedge statement is true if even one side of it is true. So given that P is true, P wedge Q must be true too, no matter what Q is.
So I could put tilde Q here.
So actually you could. Any formula here. Let's do an example.
Okay.
So suppose we have a line of a proof that's W. So call that P. So according to addition, I could infer from that, let's call this line N. I could infer from that W and then wedge, and then I could put anything here I want.
Anything. A lot big or small.
I could put a big formula there, a little. So I could put not H if I wanted. And when you add something, do you have to add something that's up in the premises?
No, not according to what you're saying.
It could be anything, couldn't it?
Yeah.
It doesn't even have to be in the premises. Because if P is true, P wedge anything's true.
Sure.
So the Q can be anything. It doesn't even have to be in the premises. And the 4th and last rule in this little demonstration, then we're going to do a proof with them,
Okay.
is called constructive dilemma, abbreviated CD. and it says that if you have a statement of the form P horseshoe Q and another one that's R horseshoe S and a third statement that's the P part of this one and then wedge and then the R part of this one, the rule says that from three statements that match those forms, that instantiate those forms, you may infer the statement that's formed from the Q part of this one, wedge the S part of this one, which would be Q wedge S. That's called constructive dilemma. Here's an English example of this. And when I say it, it'll sound obviously valid. If we go to New York, then we'll visit the Empire State Building. If we go to Seattle, then we'll visit the Space Needle. We're either going to go to New York or to Seattle. Therefore, either we'll visit the Empire State Building or we'll visit the Space Needle. That should sound valid to you. It can be proven valid. But there's 4 more inference rules, and should we do a proof with them?
Sure.
Okay. So, suppose I start out my proof, I have an A and B as a premise. Let's see, what do I want to get? I have to create this so that it's valid, of course. How about this? And let's just have as our conclusion S wedge U. How's that?
That'll work.
Okay.
That uses 3 of the rules.
Okay, we're just going to use 3 of the 4. We're saving the 4th for the next one. What would you do first on this?
Well, when I see conjunctions, I usually find it kind of easy to think about simplifying them, like write fruit off a vine. I probably don't need the Z. I don't see it too many places, but I see O's being used. I'd pull out the O using simplification. I'd probably pull out the B using simplification.
Good.
Because I see B's and O's there, I might be able to use them.
That's exactly the way I think about it when I do a proof. I look for patterns that apply or correspond to the rules that we've learned. When I see that a pattern fits, I bring something down. And simplification is the most obvious one here. And we see that simp fits this line here. We see that simplification fits this line here. In fact, that's all we can start with, isn't it? So let's do that. So Mark wanted to bring the O down by simplification on 4. So what we do is simplification says if you have a statement of the form P ampersand Q, so we look at line 4, that's of the form P ampersand Q. P is replaced by O, Q by Z. Ampersand remains in the middle as the main connective. So if this is P ampersand Q, we brought down the P. That's all we did. The justification cites the rule we used, and the line or the lines we applied that rule to. So we use the simp rule applied to line 4, so we write simp 4. And then Mark wanted to do the very same rule on 1. So he sees that 1's the simplification pattern. You want to bring down to B?
Because I see B's elsewhere, and maybe I can use them.
Okay, so line 1, again, is of the form P ampersand Q. And simp says if you have a statement of the form P ampersand Q, you may bring down the P, or if you want to, you can bring down the Q. So from P ampersand Q, we inferred the Q. We write simp, the line it was applied to. And so now we're looking for more patterns, aren't we? Not using the conclusion, but using anything we've inferred from the premises, plus using the premises, we look to see if there's anything more we can infer. Well, do you see anything more?
Well, what I tend to do is I tend to look at the new information I pick up. One, it's small. My mind is small. I like looking at small things. Small is beautiful. See, it's easier for me to understand. And I try to see if they will fit somehow. Will this O work up someplace? Well, I see it here, but I'm not quite in position to do anything with these two yet. I see the B working, kind of connecting up here. I think, there's a modus ponens there. And once I see an opportunity to use one of those rules, I'm going to go ahead and do it. So I do modus ponens on 2 and 6.
Very good. That was a ladybug. So modus ponens on 2 and 6. So modus ponens says if we have P and we have P horseshoe Q, we can bring down Q.
Now give me tilde G.
And so P horseshoe Q, modus ponens says bring down the Q. So we'll bring down the Q and we'll write modus ponens, and we applied it to lines 2 and 6. And so that's going to justify that move. Again, modus ponens from P and P horseshoe Q, the rule says bring down the Q. All right?
I know this doesn't always work for all the problems, but I'm noticing, even though I can use lines more than once, I've not used lines 7, 5, and 3 yet. And I tend to look at the lines I haven't used, because oftentimes they work together. And when I focus on 3, 5, and 7, I see that I can take these two, 5 and 7, conjoin them to fit this pattern, which will allow me to do a modus ponens, and that'll move me forward.
Okay, so let's do that.
We'll do a conjunction and then a modus ponens.
So Mark is seeing that he can take this and this, the O and the not G, and form them into this. And then he thinks ahead and sees that if he has this on a line, he can get this. And that gives him the S, and that's good. It's always good when you can bring something down. So we're going to scrunch it in here. So I'm taking the not G from here and the O from here, and I'm conjoining them by the conjunction rule, which says if I have a line that's P and a line that's Q, I can put them together. Actually, the order doesn't matter. I have a line P, a line Q. I can put them together with an and between them, and that's following the conjunction rule on, what was it, 5 and 7?
5 and 7. And then the modus ponens.
So, do you see how we got this from this and this? All right? And then Mark notices that this matches this. So this formula here matches this one here, and he saw the modus ponens pattern, which is P horseshoe Q. So from P and P horseshoe Q, we're allowed to infer the Q. All right, so we bring down the S by modus ponens. What lines?
That's 3 and 8.
Modus ponens was applied to lines 3 and 8. And so we now have inferred S from 8 and 3 by the modus ponens rule. Now it's time to take stock of where we are. We're trying to reach the conclusion, which is S wedge U. A lot of ladybug action going on here.
Since we have S in line 9, it doesn't really matter what this is. We can just pull this out of thin air, so to speak. We can add it to this using the addition rule. Since what we want is S wedge U, let's just add the U using addition.
Yeah, in other words, addition says from S, from a line that's S, I can infer a line that is S and then wedge, and then I can add anything I want here. And it doesn't even have to be in the premises, does it? Yeah. It could be any formula I wish. Because if S is true, S wedge anything is true. Because a wedge is true if one side of it's true, regardless of what the other side is. And so I'm going to add, even though U isn't in the premises, I'm going to add U using addition from S to S wedge U. So we go addition on what?
9.
And that's a perfectly valid move. If S is true, certainly S wedge U is true. We've reached the conclusion, so what's that mean?
We're done. It's a valid argument.
We've proven it's a valid argument, so thank you for your time.